BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers.
So I hope everyone is having a great time at BSides DC. Yeah? Awesome. Awesome, awesome. Well, thank you all for coming to my talk. So my talk is called Perfidious, Make PE Backdooring Great Again. Now, I'll be sort of proposing a technique that could be used to backdoor PE files that is better than the rest of the techniques, but I want to make sure that you keep an eye out for the bigger picture, which is the library that I'm sort of developing. And this is the URL that you can use to download the slides. And I know it's a tiny URL, but you can use preview.tinyurl if you are worried that I might be doing something malicious, right? So it's a good resource to sort of have a reference for the PE file structure. So yeah, so let's get started. So something about me, my name is Shreyans Devendra Doshi. I am a cybersecurity graduate student at UMD. I am also a graduate teaching assistant for the reverse engineering course there. I have previously worked as a malware research intern at Cybrary, where I sort of started creating this project. I like reverse engineering and malware analysis, and these are my contact information. So that's enough about me. Something about yourselves. So how many of you all are interested in malware analysis, reverse engineering, that sort of thing? Awesome, great. So before we get started into what this project is and what this project aims to do, it is important to understand how this project got started, right? So during the summer of 2019, that's May to August, I started working at Cybrary as a summer research intern, and the original idea that my mentor proposed to me was to basically create a framework that could be used to generate new malware samples out of the original malware samples. So his idea of how he would go about doing this was have source code of the malware samples and train a machine learning model to learn from those source code to generate new malware source code. Now I had 3 questions for him. The first one, is this even legal to do? Because I'm an international student, I don't want to get arrested by the FBI or something, right? So the second question was, how would I go about finding all these malware sample source code? He used to work at NSA, so I figured he might have access to something that I don't. But apparently he thought the zoo repository was a repository where he could find enough samples to train a machine learning model. Turns out it's not true. Haha. And after that, he basically joined another company 2 weeks into the project, and he left me to do whatever I wanted to do with it, right? So basically, I had an idea of a project, nothing to go on with it about, and I had no idea how I would even complete this internship. So one of the main fears that I had was maybe I'll get fired along with him, but that didn't happen. So apparently I had to do something. I had to create a project that could be a possible conclusion to the work that he initially began. So that is where Perfidious came into picture. So before we get into what Perfidious can do and what it is aimed to do, it is important to understand what a PE file format looks like, right? So this is a basic overview of any PE file that might exist on your machine. It can be a DLL or it can be an executable file, right? So we have the DOS header, we have the DOS stub, we have the rich header, which is sort of unknown structure until 2015. We have the PE signature followed by the actual NT header, which is composed of file header and the optional header, which points to the data directories table, followed by section header and then the actual sections which contain all the information that is required for the PE file to run, right? So a few things to remember. These are some of the concepts that you need to know before you can work with any PE file, before you can create a parser sort of a thing for a PE file. There is something called a raw address, which is the actual address at which a particular byte exists inside a PE file. So a PE file is nothing but a stream of bytes, right? You need to know where a particular byte exists. That is the raw address of that particular byte. Raw address space is usually begins from 0 because 0 to the actual file size is the actual file size of the file. Virtual address. So virtual address is the space where that particular byte will be loaded in the virtual memory once the PE file is run. Virtual address space usually starts at that hexadecimal address, but that's not necessarily true. It's usually that address for most PE files. Relative virtual address. So this is something that the PE file does. Most addresses inside the PE file, like the metadata for the PE file and everything, has addresses listed as an RVA or relative virtual address. That is the formula that you can use to calculate the raw address from the RVA if you have the RVA. This is important because when you're trying to parse a PE file from the individual structures inside the PE file from the PE file, it is important to know the raw address of a particular structure. Only then you can extract that particular structure from the PE file, right? Awesome. So this is what the DOS header looks like. It contains a ton of different information, but the most important ones are highlighted in yellow. So there's the eMagic, which is the MZ signature that is present at the end, at the beginning of the any PE file. You have the csum, which is the checksum of the PE file, and the ELF new, which is the pointer to the actual PE header, like the beginning of the extended header, right? The NT header. It points to the beginning of the NT header. You have the DOS stub. So DOS stub contains a $terminated string, which is usually this program cannot be run in DOS mode. Now, a quick question: how many of you all have participated in Flare challenges before? Right. So if you know, there was a Flare challenge in 2016 which contained an executable. Like once you reverse engineered that executable, you got the flag, and the string before the flag was this program cannot not be run in DOS mode, right? So what it was an entire DOS program that was contained inside that PE file, right? So there can be an actual program that this DOS stub contains, so it is a very important structure. Then we have the rich header. Now, rich header was originally unknown until 2015. This data structure, like there is sort of a conspiracy which says that this data structure was used by Microsoft to identify various malware groups, because since this structure was unknown, malware authors basically never thought of changing the data that was present in this structure, and this structure basically contains data about the compiler, the linker, and all those information that all those programs that were used in order to compile this executable, right? So if you forget to change this data structure, you basically have leaked all the information about the tools that you used in order to create this malware sample, right? So this is quite an important data structure to change if you're creating malicious files. This is followed by the PE signature. Now this marks the beginning of the PE file. Now according to me, you don't really need the data structures that are present before it, but because of backwards compatibility, Microsoft hasn't really lost all that data structure. This marks the beginning of the PE file, PE followed by 2 null bytes, right? Now next we have the NT header. Now NT header is composed of the file header followed by the optional header, and that points to all the data directories table. Now the file header. Now file header is composed of all these fields. Now these fields are really important. Now how many of you all know what UWP stands for? Yes, sir.
Universal Windows Platform?
Exactly. So UWP stands for Universal Windows Platform. Now what Universal Windows Platform means is Microsoft aims at developing a universal API, a common API for all its applications that could be used to develop applications for various devices that Microsoft wants you to run its executables on, right? So for this, for you to be able to do something like that, you need to support all those different architectures as well, right? So the machine field basically specifies in bytes the machine that this particular executable is meant to run on, right? So that is followed by the number of sections. This specifies the number of sections that will exist inside the PE executable file. Now there is a very common technique that you can use to add sections, right? So this field becomes particularly important to understand, because once you add or subtract a section from a PE file, it is important to change the corresponding value inside this particular section, because most endpoint detection systems will try to check for these things, like the number of sections actually match this particular field, and that is how they can easily recognize whether a particular PE file has been tampered with, right? The time date stamp. How many of you all know what that time means? Wow, you are old. Nice. So epoch time basically marks the beginning of the, you can say beginning of time for us, right? So time date stamp is basically a time delta between that time and the time when this particular executable was compiled, right? So using that time data, you can basically calculate what this time could be, right, when this particular executable was compiled. But since this field is relatively known, most malware authors remember to change this particular time. So then we have pointer to symbol table, number of symbols, the size of the optional header. Now this field becomes important because these data structure are present as a stream of bytes, right? You need to know where one data structure stops and where the other begins. So size of optional header becomes really important in that way. Then we have characteristics of the PE file, which basically specifies whether it's a DLL or an executable or something like that, right? Now optional header. Now even though it says that it's an optional header, it's not really optional in nature because it has a ton of information that needs to be used. Base of code specifies where the text section of the PE file starts, right? This is important because you need to know where the code actually starts from, right? Image base specifies the actual address at which this particular executable will be loaded in the virtual memory. Then we have a ton of those fields, and that is followed by a data directories table which contains the size of the data directory and the RVA at which a particular data directory will be loaded, right? So when we come to data directories, there are a ton of different data directories that are present, right? These are sort of all the common data directories that might be present. We will go through some of them but not all. Export table. Export table basically contains information about the exports of this particular exe file, right? Now, it's not common for most exe files to export some functions, but for DLLs it's very common because since it's a library, it will export a ton of functions that might be loaded by different exe files, right? So this table basically contains information about all those exported functions. Import table. Now this import table becomes very important in terms of exe files or malware because it gives us information about the functions that were imported by this particular malicious file. Next we have the resource table. Now when we talk about PE files, not all PE files are actually malicious in nature, right? Some PE files are actually games that we might play. So these games contain a ton of resources like dialog boxes and maybe images of guns. So all those resources need to be accessed when this particular PE file runs. So the resource table contains addresses to all those resources located inside the PE file. We have the exception table. Now exception table is usually something that is not present because it gives you information about what exception will be executed under what condition. So this table is usually scrapped from PE files because so it can be used to trigger sort of exceptions that we might figure out from this table, right? Same. So how many of you all know what certificate table might have? Yes?
Code signing certificate.
Exactly, code signing certificates, right? Now this becomes important because it says who is the author of this program, right? Who actually signed this program when it was created. Now how many of you all have encountered this dialog box which says that this program was not signed by Windows or Microsoft, right? So this is triggered because the exe or the DLL that you're trying to load or run was basically not signed by Microsoft as an author, right? Now this can be bypassed if say you have Microsoft's code signing certificate. Yeah, good luck with that. Yeah. So if you maybe found those certificates, you can basically sign your executables using that and it would never show up, right? That dialog box would never show up, it would just run. So debug table contains a lot of debugging information, so sort of the breakpoints and debugger information that was used to create this particular file. This is also stripped so that you cannot know what kind of breakpoints were used. Then we have TLS table. Who can tell me what a TLS table, like what is TLS table, like what would it have? Yeah, exactly, thread local storage, right? It's not the TLS for the networks, it's thread local storage. Now why do you need thread local storage? Most operating systems, most modern operating systems are basically multi-threaded in nature, right? So you need to be able to store all these information for all these threads separately. TLS table basically stores all that information for each and every thread, right? Next we have the import address table. Now without going too much into what import address table is and what it does, it's basically a substructure for the import table and it contains information same as the import local table, but once it's loaded in memory, it contains the actual addresses of all the imported functions, right? Now next we move on to the section header. Now section header is sort of the metadata containing structure for all the sections inside the table. Now it contains name, the virtual address of a particular section, the size of raw data when it is present on the actual file system, pointer to that raw data, and sort of characteristics. Now who can tell me why we need characteristics for any sections? Like why would we need that field?
Read, write, execute.
Exactly. So one of the common use cases for characteristics is to find out whether a particular section is readable, writable, or executable, or contains all those three informations or any of those combinations. So next we move on to the current code injection techniques that exist for most PE files, right? Now one of the most common code injection techniques is custom section addition. Now how many of you all have done OSCE before? Okay, so one of the techniques that is taught in that particular certification is how you can add a custom section at the end of the PE file and basically change the entry address of that PE file to point to that section, so that that section is executed instead of the original text section, right? So what you do is basically you create malicious shellcode, put that as a section and append it to the end of the PE file, and then change the entry address of that inside the PE header to point to that particular section, right? But it is important to know that you also need to give execute permissions to that section, because by default only the text section has the execute permissions for most common PE files, right? Now what are the disadvantages of this kind of an approach? Now it's very easy to detect for most endpoint detection systems, since text section is usually the only section that should have execute permissions. It is also difficult to do it correctly, since you need to change a lot of different fields inside the PE file. So the ratio of the stealth gained versus the time required for successfully implementing this kind of an injection technique is way too low, right? Since it's easily recognizable. The next approach that exists is PE code caving, right? So what we can do is we can find out all the code caves that exist inside the PE file. Now who can tell me what a code cave is? What could a code cave mean? Anyone? So code caves are basically streams of null bytes that are present inside the PE file which are not actually being used by the PE file, right? Now those null bytes can be used to store our malicious code, right? So it's important to understand that this is a really stealthy technique, since there would be no way of knowing whether a particular file has been injected with malicious code, and it's really difficult to implement. Now why would it be difficult to implement this technique? Now what could be the problems that you could face when you are trying to implement injection using this technique? Exactly. So one of the important disadvantages of this technique is you need to first be able to find a code cave that is large enough to store your malicious code. What is the next thing that you might face when you are trying to use this injection technique?
You need to get that code to execute.
Exactly. So it's important to know that this particular code cave needs to be present in a section that has execute permissions, right? So if that particular section does not have execute permissions, your code will not run, right? Even though you found a code cave that is large enough to store this kind of malicious code, right? So this technique imposes a lot of restrictions in terms of what you can do with it, right? So why not just edit the .text section of a PE file? Why is that not possible? Text section contains the code, right? So why not just edit the .text section? What could be the problems that you could face when you're trying to do something like this?
Tables won't line up.
Say you could do that. What is the most basic problem that you could face? No, you could edit the signature as well. The most basic difficulty that you would face when you're trying to do an injection using this technique. Yes? Yeah, so that's one of the problems that you could face, but the most basic one is that usually text section is the first section that is followed by the section headers. So when you change the .text section, you need to make sure that every section that follows it is also changed to accommodate those changes in the text section, right? All the addresses and everything would change as well. So this is not really possible until now, because you don't have complete access to the PE executable, right? You do not have complete access to each and every data structure that is present inside the PE file. So this is what Perfidious aims to do, right? Perfidious can be used to fingerprint the PE file, convert it into a class-based data structure in Python. Then you can use a function to directly input the malicious code inside the text section, right? It would extract the text section, place the malicious code using jumps inside the text section, and then the text section would run the graphical user interface, but in the background it will also run the malicious code, right? It will obviously not function as the same as the original executable, because the code paths will be different, but you will still get a GUI if there is a GUI application, right? So that is what it aims to do. Now the advantages of this approach: it will be relatively difficult to identify the shellcode, since the shellcode is not present entirely inside the PE file. What you have is chunks of independent shellcode that are connected via jumps, right? So it would be really difficult to develop a signature for such kind of executable, right? The malicious code itself is split into smaller pieces, so you can join those smaller pieces via jumps. All the other parts of the PE file are left relatively unchanged. So how would you detect these such an injection technique, right? One of the most easy technique is to only allow whitelisted software on your network, right? That is the most easy technique. Second technique that you could use is you can perform dynamic analysis of each PE file that is on your network. That way you can find out the real functionality of that PE file. The third technique that you can use is graph hash analysis. Now this is a technique that I found out about recently in Singapore at the Hack in the Box conference. So at that conference, one of the researchers basically proposed a technique that could be used to perform a graph hash analysis, right? You could create a hash value for the control flow graph of a particular PE file, right? If you create such an hash, that hash can be used to compare the distance between that hash and the hash of the original file, and you can find out whether the functionality of the file has been changed, right? That is how you could basically try to determine whether a particular file has been injected using this technique. Now, I'll give you a small peek into what Perfidious does. So this is sort of how you'll be able to use Perfidious. You can import the PE structure from PE class from the Perfidious library, and then you can say basically import a PE file into that particular structure. It will parse that structure, and then it will basically create a class structure of that, and then I'll just show it to you. Yeah, so what it does is it basically tells you what kind of structures exist inside the PE file and what kind of structures do not, and it basically, when you say DOS_stub.message, it basically prints the message that is present inside the DOS_stub structure, right? Now, this is what I aim to do with this particular library. So you can basically say that, okay, I want to change that structure and that particular field to say something else, right? I wanted to say BSides DC 2019, and then I'll show you that it actually can do that, right? So the original structure which said this program cannot be run in DOS mode now says BSides DC 2019, right? So this is what I aim to do with this library. I want to make each and every substructure that is present inside the PE file accessible so that they can be changed and altered however I want, right? So this is something that I aim to do, the future of this project. Now I am currently in the process of parsing each and every data structure inside the project. I aim to complete that by December end, and from January I'll be basically starting to find out all the links between every data structure, so that when you edit a single data structure, the corresponding field inside the actual PE file is also edited to correspond to that data structure. Once that is done, I'm trying to, the final goal of this project is to develop a program and framework that can be used to make a PE file look like some malicious PE file or a PE file from a malicious APT group, right? So the techniques used by the APT group can be used to make a malicious file look like that APT group. Now, the implications of such a tool is basically you can make a file from one APT group look like another APT group, right? That is what the next 6 months from January will look like, right? I'll be starting to develop a machine learning algorithm that can do that. So thank you for your time. That's my presentation. And any questions? So I have these backdoor and breaches card games for anyone who asks some good questions. I'll be handing them out. Yes?
Is the code anywhere out yet, or are you doing any projects like that to help the community?
Yes, so this entire program will be open source in January once I complete the parsing stuff, because that is something that I want to do for myself and learn what the PE file structure actually, how each and every data structure interacts with each other. But from January, I'll be taking on open source volunteers who want to contribute to this project. Ah, yeah, that would be great. Nice. Yes?
This seems similar to Shelter. Are you familiar with Shelter? Shelter project?
Not really, but I'll look into that. Thank you. Yes?
Do you happen to know what the cryptographic process is for signing the PE files? Because, for example, Microsoft's been signing PE files for years and years and years. They probably were using a weaker key back in the day, but for backwards compatibility, they have to allow it.
So I'm not really sure about that, but from what I understand, you can basically change the field to represent it being signed by some other, yeah.
So why Follow-up question.
Yes.
Why, if you're signing the executable, would you modify the headers or the text, for example? Why it's not breaking the signature?
So it will break the signature. What you'll have to do is, when you change the executable, you will also have to manually calculate the checksum and each and every field that represents the checksum. So there are multiple checksums that are present inside the PE file, right? You need to make sure that your checksums basically correspond to the changes that you have made in the PE file. So that is something that I aim to be like. I'm trying to make a function that can automatically do that for you. So once you make changes to any of the any of the subheaders or any of the fields inside those structures, the checksum would automatically be calculated. But yeah, that is.
It will break the signature anyway, right? Because
yeah. So if you
the hash of the binary, so the binary will change, the hash will change, therefore the signature will break.
Yeah. So if you check for the hash with the original program, it would basically be different, right? So that is one of the that is sort of like you only allowing whitelisted software on your network, right? So that is one of the important setbacks for this process. So if you only allow signed binaries that you actually verify, then you can basically not allow any code injection techniques, right? You would have software from the original author running on your machine, but not all that's not true for each and every machine in the world, right? Not everyone does that. So yeah. Yes.
How much of your implementation is specific to x86 and x64 versus what we're working on?
So currently I'm only working on x86 and x64 types of binaries, since that is what I have studied until now. But yeah, once this project gets steam, I might have support for ARM as well. Awesome. So.
Question over here.
Oh, yes.
So I'll provide speak up because my voice is low.
Yes.
How long have you been researching this topic, and about how long did it take to develop the tool?
So I'm still developing the tool, but I have been working on this project since start of May. Yeah.
Just you?
Sorry?
Is it just you?
Yeah. Currently it's just me, since I was the only intern working on this project, and I have sort of asked them to allow me to work on this project since I stopped working for Cybrary in August. But yeah, they said, yeah, go ahead. No one wants to work here.
The NES, is it open source already?
No, it's not open source. So it will be open source sometime in January once I complete the parsing phase of the project. So I need help understanding the linkage between the data structures. So that is when I'll take on volunteers and for the machine learning part of the project. Yeah. Yes.
Do you realize this is going to make execution of a lot more difficult?
Yes.
So why are you doing this?
Yeah, so that was one of the initial implications. Like, that is what my manager told me, that why are you creating a tool that could be used destructively? But my understanding of this is, once I create this framework, it could be used to develop even better signatures, right? So I'll just show it to you 1 second. So if I So what I'm doing is I'm developing checksum for each and every individual data structure inside the PE file. So this can be used to develop better signature checking mechanisms. So you can check for each and every data structure present inside the PE file instead of the entire PE file, right? So what you have is, you have signatures for every little thing that is present inside the PE file. This can be used to find out exactly what data structure was tampered with, right? So that is my aim, right? To develop a tool that could be used to develop better signatures and better detection mechanisms, along with learning. Yeah.
For the code jumping section, wouldn't you say, you said the hash graph would be one way, wouldn't you also be able to look at like the statistical deviation of jumps?
Yeah.
Because most of them probably don't jump that much.
Yep. Yeah, that can be used as well. But say you are splitting the malicious code into only 3 or maybe 2 parts, right? Then you will not have as many jumps.
Right. So number and distance of jumping.
Yeah.
Excuse me, over.
Yes.
So why do code keys even exist if you could use it to turn something malicious?
Sorry?
Why do code keys exist if you could use it to make malicious?
Yeah, you would have to ask Microsoft about that. Yeah. Yeah, like why do we even have DOS stub or DOS header anymore? Like no one is running DOS files, right? At least from what I know. Yeah, so Microsoft is basically trying very hard to make sure that all its programs are backwards compatible, and that has essentially led to a structure which is vulnerable in nature, right? Like how many years has it been since PE files have existed? We have not been able to secure it yet. That says something about it. Yes?
It's not just PE files, it's like NTLM patches and stuff for backwards compatibility. They really killed Microsoft security.
Yeah, so I haven't looked into that. I'm only working on PE files currently, but yeah. Any more questions? Awesome. Thank you for your time, and a shameless plug. So I am looking for full-time cybersecurity entry-level positions starting May 2020. So if any one of you have any openings in mind, feel free to share them with me.